All right, we'll get started here. I'm sorry, I forgot my microphone again today. I hope you guys can hear me okay. We left off on Wednesday. This is from the afternoon lecture, but I think we ended up with something similar. And I just kind of described the setup for a Gibbs sampler or a kind of a sampler that's a hybrid between a Gibbs sampler and the Metropolis algorithm, where we are treating the parameters, the hyperparameters of the prior distribution as random variables. Okay, and so we said the joint distribution, excuse me, I'm sorry. I don't know why my, okay. So we're saying the joint distribution between theta, alpha, and beta is proportional to this, the likelihood of our data, y given theta, and theta given alpha and beta, and the prior distribution of alpha and beta. And we said we're going to just put an uninformative prior on alpha and beta. So in this case, uninformative would just be kind of a flat prior, and I think that's okay. So let me see if I can go back a few slides. So in our okay, so this was our diagram. We said, we've got some parameters, alpha and beta, and for each rat experiment, or for each player, baseball player or whatever, we generate a theta value. Okay, the theta is going to be the probability of developing tumors for each rat experiment. There were 70 different experiments. Or it could be, the probability of getting a hit if, and we do this, and we would have a different theta value for each baseball player. Okay, so we're pretending, if we're thinking of the baseball example, we're saying there's some, universal distribution for all baseball players whose, the batting average is between, some number and some other number, and players are drawn from this distribution that determines the universe of baseball, and each individual player has a theta value, has their own theta value, okay, which is, hidden to us. We don't get to see it, but by seeing how often they actually hit the ball, we can kind of get at that value, okay? Same thing with the rat tumors. We're saying there's some universal distribution that says, in this experiment, this proportion of rats will develop tumors, and and any individual experiment is going to be kind of determined by those things. And we said, well, we want to include alpha and beta in our inference, right? We said we didn't want to just arbitrarily select some number for alpha and some other number for beta, because that feels a little bit weird, and we want to be able to model that. Okay, and we said, okay, in order to do that, we have to create the joint distribution of theta, alpha, and beta given our data. And we did, we didn't really do too much math. All we did was we just factored using the rules of probability. We said, the joint distribution of theta, alpha, and beta given y can be factored into this. The joint distribution of theta, alpha, and beta multiplied by the conditional distribution of y given theta, alpha, and beta divided by the probability of y. And so, it's going to be proportional to this. This in of itself, we can get rid of the alpha and beta terms because it's just going to be y given theta. And then we can factor out the probability of theta, alpha, and beta into theta as determined by alpha and beta. This would be the beta distribution. And then this, our prior distribution on alpha and beta, which we're going to use an uninformative prior, which is basically going to be flat and, kind of constant, and say, basically all possible values of alpha and beta are possible. We might have to say only positive values of alpha and beta are possible, but in that, if you imagine a two-dimensional surface, it's just going to be, in the positive quadrant for alpha and beta, it's just going to be a flat surface for everybody. All of those values are possible. Okay, and then I said, if we want to code this up, it would look something like this, and so I coded it up, and let's take a look. Okay. Where did I put it? Here. Let me. Start up RStudio, and I'll explain. Okay, so this is just the tumor data. It's just a bunch of numbers, 70 values. This Y would be how many rats developed tumors, and N is how many rats were in the experiment, okay? And so, in experiment 1, the the ratio of tumor development is going to be Y over N, and I think these are just sorted from least to greatest. So in some experiments, 0% of the rats developed tumors, and in some of the other experiments, 37% of the rats developed tumors. And probably the true value is somewhere in between. We can create a histogram. I already have the line here. Okay, and we could see, most of the values are under 30%, kind of with the mean somewhere around here. Maybe if I reduce the breaks to something like 10. Okay, this is kind of our distribution on the different proportions that we observed across the 70 different experiments. So there were 70 different experiments, and in each of these experiments, sometimes many rats developed tumors, and in others of them, none or a few rats developed tumors. And this is kind of the distribution of the different proportions, theta. Okay, and if we create a density plot, we can see, most of it's concentrated kind of around, 18%, 17%, something around there. I don't know. Okay. We can also do it for baseball. There is a data set, our package called Lawmen. It's known as the Lawmen Database. If you're into baseball, this is a great thing. It's a huge table. There's been lots of baseball players, and there's one for every single season. So I just arbitrarily picked the year 2010. Okay, and in baseball, you'll have like a 40-man roster. Okay, but only 9 people are going to be on the field at a time, and so a lot of the people, these are pro MLB baseball players, but a lot of them only play a few games. Okay, and then if you're a pitcher, you might, if you're in the National League, you have to go up to bat, but your batting average is going to be terrible, right? In general, unless you're Ohtani, so anyway, I just set some conditions just so we get kind of only batters, and so these, I said, I only want batters who had over 40 games, and batters who had at least 50 at-bats, okay? And by having over 40 games, we reduce a lot of people who are just kind of pulled up to replace somebody who was injured or something like that, kind of your second string and third string baseball players. And so anyway, I say, okay, N will be the number of at-bats. Maybe I should flip these around. Y will be the number of hits. N will be the number of at-bats. And so your batting average is going to be hits divided by at-bats, okay? So even though I say, oh, I only want to look at the year 2010, I still have 436 values here, okay? If I said, like, for the whole thing, we would get way too many numbers, and our sampler would get bogged down. Okay, and if I plot the density of the batting averages, you can see it's kind of centered between 0.2 and 0.35-ish or something. This is our density this is our empirical density. This is what we see in the data, right? And again, the big picture here is we are saying I'm not comfortable. Like in the homework, we said the shape parameters for your prior beta distribution was I think this arbitrarily selected numbers 81 and 219. I wouldn't say arbitrary. They were kind of like educated guesses. We said 81 and 219, but you might have a lot of students rightfully said, why did we pick those numbers? Okay, and so I guess we'll go ahead and move forward with the baseball data. Okay, and so let me show you how the sampler will work. Okay, so the total number of values I have is 436. Okay, I got 436, and I'm going to create a vector of thetas. Okay, and there are 436 batters in my data set, and each batter has their own hidden, like, true batting average, right? So one player had their, like, if somehow we could stick them in the baseball analysis machine, it would say this person's batting average is 34% or something, 340, okay, 0.34. But of course, that machine doesn't exist, and we don't actually know. And the only thing that gives us an indication of what their batting average is their actual performance in baseball. And we see how many times did they go to bat, how many times did they get a hit, and we do that. Okay, so there's 436 different theta values that we have to estimate, and that's going to be right here in theta. And then I'm going to just arbitrarily start off with alpha and beta equal to 1. And, keep in mind, when we did our homework, the alpha we used was 81, and the beta we used was 219. So in these initial values of 1 and 1 for alpha and beta, these are terrible numbers, okay? They're terrible numbers, but our Gibbs Sampler should theoretically get us to the appropriate region, okay? All right, K is going to be the number of iterations. And so we'll keep track of our theta values, and I'm not keeping track of the history of the theta values, but I do want to keep track of kind of the history of my alpha and beta estimates. And so I'm going to have a 7,000 by 2 matrix, and I'm going to just fill it up with zeros in the beginning. Oops. Okay, and so when we do our sampler for theta, we can derive the full conditional distribution. It's not very hard because we understand the kind of the Bayesian posterior distribution. We know that where do we have it? Theta. The probability of theta given alpha, beta, and the data is going to be, beta drawn from alpha plus the number of yeses, comma, beta plus n minus the number of yeses, right? So I think this has been made clear. And so we can use a Gibbs Gibbs Sampler for this, okay? And we can do this for all 436 values of theta, okay? Which is much more efficient than trying to use the Metropolis algorithm, okay? Because for the Metropolis algorithm, we'd have to kind of propose, calculate a acceptance ratio, see if we should accept it or not, and move on, okay? Here we can sample from the full conditional distribution of theta given our data. Meanwhile, we said the full conditional distribution of alpha and beta, that's a little bit more complex. You can do the math and figure it out. It's possible. But one of the nice things about Monte Carlo methods is that when the math gets complex, you just say, well, let's use a Monte Carlo algorithm, which if we wanted to, we could do the math, and I think it is tractable and able to do it. But I'm going to just say, okay, well, alpha and beta, what's the probability of alpha and beta given theta and y given our data? That's going to be proportional to this, and we don't know the full distribution. We only know that it's proportional to this, but that's okay, because the Metropolis algorithm only requires that we know that it's proportional up to a certain point, right? So I just have to figure this out, and then I use the Metropolis algorithm. And so this is going to be, what's the probability of all the data that we observed given all the different values of theta? So we got kind of 436 values for hits and at-bats given our 436 different theta values, okay? So that's a huge product there. And then we say, what's the probability of all 436 different theta values given this particular alpha and beta? And we get that, okay? And then the prior distribution on alpha and beta is just going to be a constant for all positive values of alpha and beta. Is it okay that I'm just saying all of this out loud? Are we following this okay? Or is this totally like... We're okay, sort of? Okay. So yeah, just to reiterate, we are able to draw theta using the full conditional because we understand the relationship between theta and the beta distribution. Over here, the relationship, the full conditional distribution of alpha and beta given our data and the other parameters is a little bit more complex. Okay, so we're just going to figure out something that it's proportional to, and it's going to be proportional to this thing. Okay, maybe I'll just write this out. Okay, so the probability of alpha and beta given theta and y. Okay, and this, keep in mind, this is a vector of theta values, one for each player. Okay, and then over here, the y, this is a vector of data, one for each player. And this is going to be proportional to the probability of y given our thing. So this is actually technically, so if we have 436 players, this is going to be the product of 436, binomial probabilities. Okay. Multiplied by the probability of theta given alpha and beta. Okay, and this is going to be kind of the product of 436 beta distribution probabilities. Times the prior probability. So this is the prior distribution of alpha and beta, okay? But we are going to use an uninformative one, which means it's just going to be a constant for all alpha and beta. Okay, so basically, I'm just going to use the value 1. Is that okay? So the probability is proportional to all of this. All right, so for proposal, I'm going to use a normal proposal. I'm going to say draw a random normal value centered at alpha with a standard deviation equal to SD, okay? And so we can specify what standard deviation we want. This is something we can tweak, okay? Because alpha has to be positive and beta has to be positive, if my R normal ends up being less than 0, I want to make sure that I will draw 0 for alpha and draw 0 for beta. I don't want to draw negative values, okay? So for my proposal, this is going to be the function. Is that all right? So if I'm currently centered at 1, 1, okay, I'm going to just draw a random value, and these are going to just say like, hey, let's try out this value for alpha. Let's try out this value for beta, okay? Maybe I want to choose a bigger value for the standard deviation, so I have a little bit more variance. And so, excuse me, it'll say, let's try out this value of alpha. Let's try out this value of beta. It might propose negative values, but we don't want negative values, so we're going to at least have a 0 in there, okay? Okay, the probability, again, is just, it's going to be the product of all of my theta values drawn from the beta distribution. Okay, so that's this part. The beta distribution, what's the probability of theta given alpha and beta? Okay, and normally I would just have a product of this, but because if you multiply the product of 436 values that are all smaller than 1, you're going to get something that is going to produce an underflow error. We can't, our computers with floating point arithmetic is not able to keep track of a number that's really, really, really small. Okay, it just says it's too small. I think it's 0. So to avoid that, we turn everything into logs, and then instead of dealing with a product, we now deal with a sum. Okay, and this is the same trick we used for, or not trick, but it's the same thing we did when we were doing the decoding, right? So is that step okay? All right, so we need the sum of the beta probabilities for each theta, and then our data is, we have 436 y values, 436 n values, and then we've got 436 theta values, and we're figuring out what's the probability of, d beta yn given theta, okay? And we get the, and we're turning them into logs, and then we sum them up, okay? So this will be the log probability of whatever alpha and beta that we've proposed, okay? Okay, so so here we're going to do 7,000 iterations, and within each iteration, we're going to have 438 values to sample. Okay, we've got 436 theta values, 1 for every single player, plus the alpha and plus the beta. Okay, so it's a huge model, right? And so if we just use straight Metropolis, we would have to propose a vector of 438 values and then calculate the acceptance and the rejection thing. It's going to be a little bit too rough to do that. Thankfully, the Gibbs Sampler allows us to sample 436 of those values from the straight conditional distribution. Okay, and I think in your homework, I hope when you did problem 2 versus problem 3, I hope you saw that problem 3 is a more efficient way to sample from the target distribution than than the Metropolis algorithm, right? So problem 2, you had the Metropolis, multivariate Metropolis, and it was only 2 variables, but you saw it took a lot longer to get to the target region, whereas when you had the Gibbs Sampler, it got to the target region faster. So anyway, thankfully, we can use the Gibbs Sampler for 436 of those values, and all we're doing is we're just drawing from the straight conditional distribution of the posterior, which is, we're asking for one random beta value, and the shape parameters are going to be the original alpha plus your number of successes, comma, beta plus the number of failures, effectively, okay? And I'm hoping we've seen the beta binomial enough for this step to be familiar to us, okay? We're going to propose a new alpha and new beta, which I'm going to call A prime and B prime. The proposed function returns a vector of 2 values, so I'm just capturing that into eta, and we take out the first eta value, and that's going to be A prime, and the second eta value is going to be B prime. Okay. Then we calculate the the ratio between the proposed values A prime divided by the current values of alpha and beta. Okay, but because it's logs, we're taking a difference. Okay, so we're going to say, okay, what's the ratio? So I guess this is the log of the ratio. The proposed value minus the current value. What's the probability of the proposed divided by the probability of the current taken as a log? I'm hoping this is okay, right? Okay, and then do we accept that, yes or no? So we generate a random uniform. We're going to take the log of that uniform value. If the log of the uniform is less than the ratio, we will take our proposed values A prime and B prime and set them to alpha and beta. Otherwise, we don't do that, and our current alpha and beta remain, and we will store them into our new into the next row of our AB matrix. Okay, and so this is the Gibbs sampler. We have, or the Gibbs and Metropolis hybrid sampler. Okay, so we have Gibbs steps for the 436 different theta values that we have, and then we've got a Metropolis step for everybody else, for the last 2, the alpha and the beta. Okay, and if we wanted to, we could have done the math to figure out the full conditional for alpha and the full conditional for beta, but I wanted to show you this setup to show that if you don't feel like doing the math, we can reduce the amount of math that we have to do and have this. Okay, so I'm going to go ahead and run this. We're doing 7,000 iterations, and with each iteration we're drawing 438 values. So it's going to take a little while, not too crazy. Okay, if I use the whole data set and had 10,000 baseball players, then it takes a lot longer, because now you have close to 10,000 different theta values to draw. Okay, so here I'm done now. Okay, and let's just see the trace of the line alpha and beta. Okay, and so what we see, so these are the different values of alpha, and we see it keeps climbing, and then when it gets to around, I don't know, what is this, 100 something, it starts going up and down. Okay, so to me this seems like the region. So maybe from about, I don't know, 90-ish to 150-ish, that seems to be the region. I probably need to tweak my choice of the standard deviation and see how much it wanders. But this kind of seems to be the region, and so maybe I would throw away the first, I don't know, 2,000 values or so for the burn-in, because we started off at 1,1 for alpha, and those were clearly bad choices. But maybe around 2,000-ish, we're entering the region of, what seems likely. Okay, we do the same thing for beta, and we see, the graphs look almost the same, except the values truly are different. It's not. So if you compare these two plots, they look almost the same. The only thing that's changing is the vertical scale. So what's going on there? What that tells us is that the only values that are getting accepted in our sampler are ones where alpha and beta are highly correlated. Okay, we don't really have a whole lot where alpha is getting bigger and beta is getting smaller, or vice versa. They're moving together. When alpha gets bigger, beta gets bigger. When alpha gets smaller, beta gets smaller. And if we think about that, that makes sense, because if we think of what the alpha and beta distribution represent in what the two shape parameters, alpha and beta, or A and B, represent in the beta distribution, they kind of represent the number of heads and the number of tails in a coin flip, right? And so if the overall proportion for something like baseball, if the overall density looks like it's strongly centered around 0.3, 0.28, something around there, if alpha is 200, then beta would have to be, close to 1,000, like 900 or something like that, right? And if alpha gets too much bigger in comparison to beta, then that would shift where the center is and whatnot. Okay, so I guess, if I decide to just throw away the first 4,000, or I don't know, first 3,000 values, we can see these are kind of likely values of alpha and beta. I don't know, we got something around 100, 130. Probably I could afford to run this even longer. Let me just, we're kind of already in the target zone. Let's just see what we get. Okay, so I don't know, quite a bit of variability here, but let's just see. So we're getting all sorts of values of alpha, all sorts of values for beta. Let me just alpha and beta. Let's ask what's the mean of this. The mean for alpha and the mean of beta is 146 versus 412. Okay. I'm going to just use those. These are point estimates. This isn't truly a full Bayesian thing. But let me just show you what, if we use the mean alpha value and the mean beta value from our kind of posterior distribution, what does our prior distribution, beta prior distribution, look like? It looks kind of like this, okay? Between 0.2 and 0.3-ish, there's a strong mass, okay? If you recall the homework, the numbers that we chosen were 81 and 219, or something like that, okay? And if we say, what does the distribution look like there? It looks almost identical, okay? So when we created our prior distribution, we arbitrarily selected some numbers to reflect what we understood to be batting averages, okay? And we said, well, most batting averages are between 0.2 and 0.35, so I'm going to choose a beta distribution that represents that, okay? When we switched over to this hierarchical model, where we said, I don't know what alpha and beta are, I want to be able to model those ourselves, we got different values of alpha and beta. We got 146 and 412, but the resulting distribution is almost the same. It's just a little bit tighter, okay? Basically telling us that if we were going to create a prior distribution on the data, we can be, pretty confident. Interestingly enough, if we do 146 divided by 81, that's the number we estimated for alpha is about 1.8 times bigger. And if I do 412 divided by 219, okay, 1.88. So the values that are kind of, and I don't want to say these are estimated because these are just point estimates, and a full Bayesian thing is we've got the distribution. But But the kind of the point estimates that we've got are almost proportional to the values that we selected in our prior distribution. Okay. Let me. If I create package hex bin. Install.package. Am I doing something wrong? Oh, install packages. That's it's hard. Okay. Library hex bin. I gotta update my R. All right, let's see what this looks like. Okay. So anyway, what we see are that the only values of alpha and beta that make sense are ones that are highly correlated, which is fine. Okay. If we did it for the tumor data, which had a lot more kind of a wider alpha and beta, I mean a wider kind of distribution of values, unlike the baseball data. Okay, I'm going to just use the same thing. I'm going to change this instead of using normal with this distribution of 6. We'll let that run. Okay, so this is for the rat's tumor data. It's done here. Let's kind of see what values. So what it finds is values of alpha. I don't know. There's this kind of seems to be the area that it's found, and we can kind of just plot what values of alpha and beta we have. So if I do 4.4 and 26.6, these are kind of just point estimates. 4.4 and 26.6. This isn't the best way to do it, but this is kind of the this would be our prior distribution of alpha, of the prior beta distribution that we would place on all of the different rat experiments. Okay, is something around here to represent that. You know, most of the rat experiments are, I don't know, produce certain values there. Okay, is that all right? This thing? Shoot, it took a little. I don't have a ton of time left over. I want to cover a neat application. Well, I don't know what I think is neat. Kind of like the way we did the deciphering thing. There's a cool thing. We can use the Gibbs Sampler for a document classification system. Okay, and I guess we'll have to talk about this next week because I don't want to start it now. But I'll post this document for you guys to read over the weekend. There's a lot of questions about homework 6 and the final exam, or the last test. I don't want to call it a final exam, but you know, we've got to have something. So I'm writing up homework 6. I think it'll be, I'm hoping it will be fun, and I'll probably make it due. I like to give you guys at least 1 week to finish it, so I'll probably release it on Monday and make it due like Monday or Tuesday of 11th week, and then for the final test, I'll talk about that next week as well. But I will say, you know, it'll be my intention to make the final test, I don't know, gentle, I guess, and I'm having a tough time thinking of good questions that will be quote gentle, but I'll release information about the final but on Monday as well. Anyway, we'll wrap up here for today. We'll see you guys on Monday. Anyway, I guess what I want to say is I don't want you guys to be too stressed about our last test. Okay, so just relax. It's gonna be I'll be nice to you guys. Okay, for our last test. And you can hold me to that. Okay, we'll see you guys on Monday, and have a good weekend.